So, as he mentioned, I'm Per Brashers. I have the honor of having no phonetically spelled name. So when I started a company, I decided to make it completely incomprehensible and start with Yttibrium. So nonetheless, what I want to do is step through a couple of things. I'm inherently a storage guy. I came from 11 years as a director of EMC. I just come off of being CTO for Data Direct Networks, a number of other positions in storage. So I will start with the storage-centric bit. Then we'll move through some of the controllers and networks, some of the good and the bad and the ugly of what goes on there, moving through CPU, memory. And then I'm going to spend a bit more time on the ambient data center. You heard a little bit from Harrison about the Open Compute. The Open Compute standard is an open source version of hardware. And I'll go through a little bit of what that is, but I'm going to go more generically on the trends towards the ambient data center and how that's going to affect you. I'm going to give you what is not in scope. On the top is basically the business processes, and then down below that is capacity planning. And these are the kinds of things that you need to work on to build and scale systems like the Facebooks, et cetera. But I'm going to go more on the IT assets, things that we actually care about in the hardware, how that affects our software, what those builds are going to look like, and then a little bit into that data center, as I said. So all the stuff on the right-hand side, if you want to talk about it, I'll talk to you later. This is a cute little picture of one of my babies. This is a sideways version of Knox. It is a dense storage provided option. It has 60 drives in 1.5U, slides into a rack, and I'll talk about the open rack. I'll talk about how this actually works. But what was needed was effectively quit using the front of the drive bay, the cabinets only. I'm going to give you a primer on where drive technology is going. And now this was written by somebody who goes in the opposite direction. So on what is your right is what's coming up next. And that's shingled media. And what shingled media is all about is the magnetics of actually writing are significantly wider than the magnetics of reading. Okay? That's the important part of it. So now I could take and build these things literally like you would build a shingle of a roof and say, if my magnetics of write are significantly wider, all I have to do is offset a couple of bits and I can write again and there's still some of the original left. Okay? That means I can come through and I can read. What that also means is, how in the world are you planning to update one of those tracks? Because if you go into the middle and you try to replace a shingle on your roof, you know you're getting out pry bars, you know you're doing some very interesting problems. This is basically going to bring disks down to their knees, and they're going to become append-only or slower than tape. That's the bad news. Gets more interesting. You go into heat-assisted magnetic recording. These two in the center are the current trajectory, one of which is to use a laser, the other of which is to use a microwave. Problem here is you lay down this nice, beautiful, flat surface of neodymium. You have to actually grease the surface a little bit so that you get a nice, even fly height, and all of those abnormalities are all wiped out. So you get all this nice, perfect stuff, and then you put a laser on there, and all that grease starts to boil off and starts sticking to your fly head, and after a couple of rotations, your fly head starts to drop onto the drive. So we have some issues to get around in the actual build of the physics, the actual how to lay the magnetics out and all of that for those drives to become useful. But once they do become useful, you'll get your random access back, random write access or update access. If you're just doing reads, okay, fine, you're sequential appending and go with shingle. And then comes the stuff that we've all been hoping for, right? So each of these, by the way, is basically roughly a doubling. Shingle is effectively going to be the 6 terabyte drive. They don't think they're going to get up to an 8. The Hammer drives are basically hoping to get to 8. And then bit pattern media is really interesting because now you quit laying down just float neodymium onto the glass substrate, and you actually get into a point where you etch the drive platters. So this does a couple of interesting things. One, it drives the cost up significantly. You can no longer do a flow-based pattern where you just merely simply flow these things, but you now have to actually go and grow them. So that's a really interesting problem because fab facilities are extremely expensive and rather short-lived. If you take $2 billion to build a fab, it only lasts about 6 years, and you basically have to make your money back in that time. So that's going to be a really interesting problem. But even more interesting was all the guys who've gotten so used to having these utterly perfect flat surfaces and fly head, you suddenly have holes, and you suddenly have turbulence. And so the whole fly heads currently are being driven into the platter above them and ripping off. So that's going to need a little bit of help. Some trends. IETF, thank God, voted down SATA 4. SATA 4, SATA, rest in peace, I will not miss you. That combined with basically the home consumer, the mobile consumer, et cetera, is effectively moving to flash anyway, right? Most of the laptops, almost every portable device is becoming a flash device. And the home consumer is effectively becoming kind of like our first bigger cloud users. They really are starting to talk about smaller drives at home with, oh, cloud backup, or hey, let me use my iCloud to get to my files. So I actually really care mostly about my provider, not about drives at home anymore. So that's kind of an interesting thing. You also see hybrid drives coming out. There's a lot of manufacturers going on and talking about, I've put flash right at the bottom of the controller. It's right attached to the drive, and it's intending to get to the concept of, if you have a sequential load, I'm going to go ahead and do a read of that whole track and populate it so I can mask off rotational misses, all of this, right? Frankly, that's not a problem we have. And so I don't believe that you'll see, these are what I'm going to call the flash in the pan later on. I don't believe the hybrid drives are going to last long, mostly because the applications already know what they need to do. And if the application can get through the unfortunate controller and get directly to disk, you now have the ability to say, I can map everything, I can prefetch better than a kernel can, and better than certainly some drive that has absolutely no idea about the application. Object storage is the next really interesting move. File systems have become kind of a pain. The pain is primarily based around, if you are limited to 16 terabytes, and that's about what regular inode structures are allowed to do, you come into weird conniptions. You get into ideas of trying to tie inode trees together by replicated master inodes and all kinds of shadow inodes, and it gets messy quick. And I'm not even going to start talking about why POSIX is just about to die. This is just like in the structure of the file system. So you see a lot of things where most of the bigger providers have already shunned the file system for large data sets and gone into some level of object storage, whether it's home written or whether it comes from a provider, like an Amplidata or one of these guys have a number of providers out there. So it's really interesting what you get to define as object storage. Does that mean it has some amount of metadata, or does that mean I'm actually, say, open brown bag, insert stuff, close brown bag, just merely simply know how to find the bag again? So there's some lots of definition coming up around that. SSDs at capacity are not really, and by at capacity, I mean a 2.5 or a 3.5 inch form factor. They're not really going to be great in my lifetime. Or at least my useful lifetime. Because if you're still stuck at a 2.5 or a 3.5 inch form factor, you're really talking about how much polymers do I have around the actual useful bits, and how much traces, et cetera. And so you get to a point where it's like the form factor itself is starting to become an issue. So you see things like, okay, I can put it on a card. Well, now I'm stuck with a 50-watt limit on a card. You start seeing things like, well, what if I just build a whole shelf and just run 2U of these things in? And so there's going to be some really interesting questions in that. But I don't think you're going to see, you know, the 12 terabyte, 3.5-inch flash drive before I retire. And again, I talked about the home consumer moving to SSDs and moving away. I mean, a lot of these people, WD, Hitachi, et cetera, are trying to sell home NAS servers that actually still have spinning media in them, and yet I've met 25 home NAS servers who, yep, they bought it with a spinning media, they pulled the spinning media out, they put solid state media in, and they said, it's quiet. My wife didn't get mad at me. Okay. And then really, there's an emergence of these cloud drives. Because there really is a shrinking and dying market for desktop, laptop kind of drives, the manufacturers basically are looking at how can they get cogs out of the drive and still make something reasonable. Now, the way they would do it with desktop or other drives would be to do things like, I'm going to get rid of 2 air bearings, and I'm going to put only a single air bearing on the bottom. I'm going to take the fly head, and I'm going to remove about 1/3 of the electronics and get a light fly head so I can actually cope with more Z-axis movement, but I can't cope with any X or Y-axis movement. Right? So some interesting problems that the desktop drive kind of came about. Really, now you're trying to push back over the side and say, you went too far, whatever manufacturer, and now get me that mid-class drive that has dual bearings, that has a little bit better fly heads, that has maybe some RV resistance, but maybe it doesn't have the full circuitry, maybe it's just part because the circuitry is really expensive, both in power and in cost, et cetera. And then I've already kind of touched on the areal density problems, so I'll kind of move on because I'm going to actually hammer that point later, no pun intended. We're not realizing the power savings. You look at the yellow line up there, which I'm sure shows up incredibly well, and that's the power per unit used, power per gigabyte, that is, on the laptop drives. And you'll notice that it goes down and down, and about 2012 it sort of bottoms out pretty neatly because guess what? People really cared about power when you had a battery. Well, they didn't do those optimizations in the 3.5-inch drive, which is really unfortunate because those drives are incredibly wasteful, and yet they're the ones at volume. And they're the ones that we have in hundreds and thousands in our data centers. Sorry to be depressing, but drive speeds stopped. In about 2000, you really couldn't get anything more out of drives. Literally, the number of megabytes per second coming off of drives just flatlined. Everybody's projections was for, we're going to get to, you know, terabyte a second off of 5 platter devices, and they kind of forgot that whole idea of it actually takes time for the drive to rotate around. Yes, it may go 7,200 times a second, or 10,000 times a second, or 15,000 times a second, but that's still a significant amount of time. And if you happen to miss what you were looking for the first time, you bind and you wait. You don't go on, oh, I'm going to pick up the next thing in queue. You sit there and go, and then the drive comes around, and hopefully you get it the second time. If you get it, but you didn't get your checksum, you will actually try it again and again and again. So one of the asks with it I go and talk to the manufacturers about is, relax, guys. Give me bad data. Let the application do some of this work. Don't sit there and retry until you finally decide, I can checksum it. I can cope with some bitwise errors on my side. Why are you spending all of this time and making all these long tail problems when you could just say, you know what, I'm going to return my best answer and you figure it out. And so they look at me like I've got 7 heads when I tell them that you can return crappy data. It's okay. Capacity growth, it's been very long history of nice straight linear growth. You know, you plotted against each other there. You can see it's just been going on. But sad news is it's flattening. What's happening is as you were saying, as I was talking about moving towards the heat-assisted magnetic recording in bitwise, it really starts to slow down. Really, the game, therefore, is changing, right? If you look into the mid here, we've just passed into the 2010 and 14, and you're starting to see the annualized growth rate is just dropping off like a stone. So you really need to start thinking about questions like longevity. Rather than, I'm going to get my cost efficiency by, I buy these things and when they still have a useful resale life, I swap them out for a drive that's double the size for the same amount of power. Thank you, manufacturers, for going ahead and giving me double the capacity at half the power, please. So now you're starting to go, wait a minute, I'm going to swap this same drive for another drive of exactly the same capacity? That makes no sense whatsoever. So now we're starting to say, a 3-year return isn't going to be good enough. It's going to be 5, 7, et cetera. So we're going to end up with a really interesting problem. And that affects the manufacturers as well. Because now we're talking about RMAs coming back in, you know, all the 80% no trouble found because the drive's gone into some weird state that you can't get fixed in the field. You send it back, they put it on their bench, they say, I don't see a problem, what's wrong? And they send it right back to you. This is just lots and lots of churn that nobody needs, and we need to be forcing some fixes to. And so I've been talking to the controller manufacturers about how can you, controller manufacturer, deal with some of these problems better. Can you actually do a better hardware reset? For instance, in the no trouble found issue, we've discovered that if you set the drive into park, right, you go ahead and actually stop the spinning, drop the 12 volts, it doesn't necessarily come back. If you then also drop the 5 volt, it does. So now the theory is more along the lines of my RV sensor is fighting with my RV circuitry, and there's a feedback loop problem. So the latest test I've asked for, and I'm hoping to get results this week, is can you just drop 5 volts, that should scare a lot of people who know what I'm talking about, and keep the drive spinning, and then come back and say, have I gotten rid of my 80% NTF? The other interesting thing about the 80% no trouble found is it's not repeatable. That same drive is almost never a repeat offender. So somebody who does cosmic ray tracing or something like this should be talking to me about how exactly we determine what these things are, where they come from. Charting over time, here's my best prediction, right? Anybody who ever makes a prediction is always held up to be an idiot later, so I am already automatically an idiot by making a prediction. But we've coming into the shingled magnetic recording basically beginning of 14 to mid 14. They're going to be viable. But after that, you're basically looking at, it's not until around 2018, that the heat-assisted magnetic recording comes in. So now you have to make a decision. Are you going to stay with the 4 terabyte drives all the way out until 2018 because you can't build something that is truly log sequential or, quite frankly, never updates a track, right? Sure. I know I designed cold storage facilities and so on. There are plenty of times where you can say, I can write from track 0 to LBA max, and I can just fill these things, and 6 years later, when they're absolutely useless, I can do it again, right? And so there are use cases, and you could effectively say the shingled magnetic recording is the use case of, I can get rid of tape. So, I'm going to bring this back around to be a little bit more contextual because I'm sure by now you're thinking, what does this have to do with me? Growth and data durability are sort of the two things that I kind of look at from a storage point of view. Don't expect capacity to change because, of course, shingled media, as I was mentioning, is slower only. The flash in the pan options, all of these guys who are coming up with flash drives or flash appliances with hybrid drives, et cetera, I don't really see that taking off. I think that that's going to be one of those problems that we should be solving in the application layer. We should be getting the controller manufacturers to be telling us more about what they're seeing underneath, exposing more of what's happening to us so we can do a better job of making our decisions. And then the big data drives are really going to be the only thing that we have which helps us try and avoid cost, right? They're going to be the cogs now that you've effectively said, okay, desktop drives go away, therefore I've got to have some, can I call it low-class drive? That's usually considered not very appropriate to language, but some kind of mid-class drive, how's that? If there is nothing below it, then why is it mid, right? Data durability, really, it's got to start at the application, right? We do very little checksumming. We do very little work in the general field to prove that the data that we have gotten back is actually good data. And there's reasons that I think that this has never happened. Primarily things like, you've got to be kidding me, I've got to waste 100% of my cores on just doing checksums for a couple of terabytes of data to prove that I've actually got the right data before I can even do anything. So there's trends that I'll show you in the next section, actually the section after next, which are basically helping us to get past that. And so I really think that there's a point where we are going to end up having to do more of that work and not have the underlying hardware doing it. And then disaggregated RAID is a really interesting concept. Distributed erasure coding or the Reed-Solomons, et cetera, have some interesting sub-properties to them. Some of the interesting sub-properties are things like repair. If you go and you spray your 10 of 14, as is favored by a previous employer of mine, and you say, I've got 3, 3, and 7, et cetera, so you've got your pieces spread out, and you have one missing, a crucial one missing. You have to read all of the 14 into one machine, go do your math, redo it, and then decide, okay, that's perfectly good, and run it out. So that's pretty painful. And Reed-Solomon isn't really the fastest and most interesting algorithm for this. The RAID guys have done some really good stuff in hardware that have kept it working quite well to some level of a degree. So now I talk to them about things like, can you create virtual LUNs? Give me 6 virtual LUNs or 17 virtual LUNs spread across these machines, and you merely simply go and do work. So we did a proof of concept just merely simply RAID on iSCSI. I mean, everybody should shudder at such a terrible idea, but it worked. It was slow, but the proof of concept is there that you can have hardware assisted, and here you get to see the dichotomy of me. On one side I say, I do not want you to do it in hardware, I want you to do it in software. On the other side I say, I want you to conserve my CPU power, and I want you to do it in hardware. So, belief is in the beholder, right? And then RV resistance, right? I was talking earlier, if we go ahead and tell the manufacturer, maybe by a parameter or some other thing that I could set at the drive level that said how much tolerance I can have for bitwise errors, then the drives can start behaving very differently. I could actually get a drive that gives me almost as many IOPS as a SSD if I tolerated all kinds of strange answers. So there's some really interesting work that should be done by somebody going around and getting these manufacturers to relax what they're giving us so that we can just basically start driving IOPS. We're not really going to drive throughput anymore because, quite frankly, there's that rotational problem. But we can drive IOPS by allowing, okay, I can get the IOPS. You may return me an incorrect answer. I have a checksum, which I can do, and therefore I can actually service better IOs from these things. All right, moving into controllers and the network. Controllers are changing very rapidly, primarily based around the concept that you can now stuff an awful lot of CPU power in something as limited as 50 watts, but secondarily by some brilliant guy who said, oh, I can take a connector from this card and plug it into the power supply and get more than 50 watts on it? Oh, interesting. So whenever that brilliant guy did, now you start getting some really neat stuff starting to happen in the world. And then networking is changing very rapidly. You know, this is just a short show of the flow diagram of OpenFlow, which basically says, if you haven't told me an update, I don't need to go ask a routing table where to go. I have it built into my forwarding table, and I'm off and running. So, Trends in the controllers, right? They're going to be much more powerful, and they're also going to be smaller. A lot of these new chipsets are coming in out of this. So if you're familiar with how they build chips, they basically take the smallest possible microns that they can for the highest margin devices, namely the CPUs. And the N-1 generation stuff is used for everything else, right? Now you're starting to see, and the N-1 is actually really very interesting. And the N-1, if you go and actually get things like the smallest transistors around for things like, ARM processor or some of these other things, they're really, really, really small, and they're using a lot less power, so they're a lot more efficient, and that's getting quite interesting. I'm making another prediction here. And that is that the bus for attaching for a SCSI, effectively, or SAS, is going to basically top out at 12 gigabit. And there's really very little evidence that anybody wants to get above 12 gigabit, partly because you're already way overdriving what the drive can do. But secondarily, at 12 gigabit, you are already not able to saturate the bus with the number of drives you can address. So where's that going to change? Is somebody going to say, well, I think we should start addressing 2048 drives with this one connector? I'm risk adverse, and I kind of think that if you're addressing 2,000 drives with one physical connector, you kind of need to see a psychiatrist. SAS switching and PCIe switching. They're in a battle, locked horns, and having a grand old time. And the interesting question is PCIe has a problem with timing. PCIe timing is amazingly painful and hard to get right. And SAS has a, hey, everything's fine, come down to my house. And of course, lots of retries, et cetera. So there's a bit of an issue in the SAS switches where they're not quite capable of doing the recovery. And then there's the problem in the PCIe switches where they're not even able to keep up with the signaling. So watch that, because I believe the war is going to end up falling over onto the PCIe side, because I believe timing is an easier problem to solve than laziness. I'm going to talk more about the PHY here in a moment, but the Xeon PHY is a really, really interesting move by Intel, which is to basically try to get away from few cores and get into significant cores, right? And then you're starting to see chipsets sold separately, right? I've talked to LSI and a number of other of these vendors who literally have been in the card business, who are starting to say, oh, you just want a chip? You can burn that onto your own board. You can actually design custom-made boards, et cetera. And this, of course, is helped by Open Compute, an open source hardware service. So this kind of move has started getting to become a normal human is actually able to buy these things. Even our Arduino is moving this direction, which makes things really interesting. Anybody who's been in the HPC space knows RDMA, loves the small message passing that it can do, and really it's starting to come to life. Believe it or not, it really hasn't been very functional to date, and it has a very significant problems with retries, overhead, all kinds of interesting issues that are now finally starting to get good breathing room, and RDMA is becoming just about as good as DMA. So now you're starting to look at, wait a minute, if RDMA and DMA are basically coming to convergence, and you're telling me I've got networking coming up in 100 gigabit or even more in these Taurus networks, you're starting to talk about 400 gigabit networking. Now I'm starting to talk about RDMA speeds on Taurus networks. I can start talking about this whole stage becomes one computer. Right? Many, many racks can now start teaming. And that's really the disaggregated rack. And so you see the move towards disaggregated RAID. Now comes the question, if my CPU lasts 4 years and my memory lasts 6, why did I throw the whole thing away when my memory was good for 2 more years? Why didn't I just take the CPU out, chuck it over my shoulder, and drop a new CPU in? Why did I do all of this? Why am I throwing the motherboard away? The traces are fine on that for 15 years. Okay, so they delaminate before that, but Here goes this side, or this side, I don't remember which analogy I did. Trusting the hardware to do something useful, T10 diff is really a very interesting idea. This means I can hand a checksum down, and the drive will check it so that I haven't actually gone and done something stupid on the wire, right? If I'm disaggregating, I better check that I didn't do something stupid on the wire. And now the drive can say, I got what you think you sent me, and then it can hand it back when I try to pick it up, and I can look at it and go, oh, yep, I sent that, that's what I got, this is what I have in my database. So now the job starts becoming much easier to say, go ahead and return incorrect data. I can check that the data is incorrect and go run my Reed-Solomon or whatever to actually deal with the bitwise errors. So this was a very interesting move, and it's only a piece of the puzzle necessary to make this stack work correctly. RAID cards are still going to lead for revenue, so we're still going to fight with manufacturers who believe that RAID is actually still alive. And then the back to glass is really interesting. Anybody who wants to future-proof their data center builds probably builds with glass in the first place and says, any new technology comes out on glass, and eventually somebody kind of smart comes around and figures out how to do it. Well, so we've got silicon photonics right around the corner. Now we've got the idea of I can put a chip that can take a, what was the promise? An electron in and a photon out, and a photon in and an electron out, and it almost took a Cray out of business. We're finally getting there. The technology is actually maturing to the point where that is not quite the correct ratio. It takes quite a few more electrons to make one photon, but it's getting there to the point where signaling rates are high, et cetera. Next prediction is you're going to see something like DWDM, where you've got 4 different laser colors all coming off of one, and your one connector, instead of being 100 gigabit, is going to be 400 gigabit, and you're starting to get to some really interesting throughputs. And then I've already talked about all of the rest of those. So again, how do you deal with this at the application level? The open socket insert stuff, closed socket, is probably not quite the way that we need our young ones to come up and out of school thinking things work. Yeah, it's going to be around for a long time because it's very, very intrinsic to the Unix system, et cetera. But really, for large types of systems, sockets and just blindly inserting things isn't really going to work anymore. We're going to have to be doing some checksums. We're going to have to be working on the data as it's in flight. Real intelligence in the controller, and I just noticed there's a timer down here that says I'm way behind. We're looking at drivers and application. Higher density solutions, right? The flash that I was talking about, and where you start getting out of form factors that we talk about today and into how many actual flash bits can I instill in a single U or 2U, et cetera. And then data durability, right? It's all about non-hierarchical topologies. So I'm going to be talking about a torus network. I'm going to be talking about a number of different styles of how do you deal with dynamic routing, how do you deal with the data durability when our old problem used to just be a torn packet and retransmit. Now, that's not necessarily going to happen, so we want to talk about, okay, if I've got something, half of it came in from one pipe and half of it came in from another, I should be able to reassemble that because I've got all the pieces. Why don't I reassemble it? So there's some efficiencies to be dealt with there. A lot of interesting things on the converged network, but let's move on. We've been very comfortable. This is the way that the world has worked for years, right? You know that at the bottom you buy drives because it's cheap and there's lots of them, and at the top there's in-memory L2, L3 caches, et cetera. This is all falling apart. It's starting to not entirely go upside down, but some of these mid layers are starting to get out. So it's kind of starting to get oblonged and weird shaped, and that's going to be interesting. DDR4 is just about around the corner, and then other type of interesting thing around the corner is the wide I/O. But really, the questions I want to talk about are, everybody who's building new style of RAM is effectively saying it should be persistent, because I can make it persistent easier than I can make it non-persistent. I hate the concept because I've got a node in a cluster that reboots nearly instantly with the same unfortunate state that it went down with. Now, if that unfortunate state happened to have been its memory state because a kernel panic, it's going to come up and go down, come up and go down. And now I have to come up with a new process for how to shoot that guy in the head. Also, it was down for an hour. Comes back and says, oh, I'm fine, I'm perfectly happy, rejoins the cluster with old data. Now we have a lot of work to do on, okay, great, how am I going to deal with these transitory problems when I've got non-volatile, effectively, memory in these things? And don't even talk about how am I going to decommission these, get them out of my data center when I have problems like I have to crush every drive in case there's any data loss. Well, now I've got to crush every DIMM? Really? 3D NAND, really, really cool. It was demonstrated just a few weeks back at the Flash Summit. I chose to take their slide, which shows how it's built, because I thought that it was actually really, really interesting on basically they're using a torus network to do their layout and just keep getting the wafers smaller and smaller and smaller, and then drive the pins down into, and these are obviously etched pins because these things are really quite small, so they don't physically, take a drive, right? But this is really very interesting because now you're talking about really dense DIMMs. We're talking about terabytes, and we're getting to a point where you can say, hey, remember that in-memory database that was being predicted? It's possible. Is it a good idea? That's a different question. More memory available on the motherboard with higher access rates, higher access times, excuse me. Really fine balance, because as you get into, I've got a bunch of memory on the machine, but the memory is really slow. Am I doing a better job by saying I actually have some portion of it in traditional DRAM and the rest of it in this 3D or other whatnot? Cost curve is so high, I talked about that already, so it takes a couple of $1 billion to build a fab, and they're not durable themselves. The heat dissipation problem, and the heat problem was really very interesting when Flash first started hitting the market. And it's really been figured out that if you, quite frankly, heat it a little more, it resets the bits. So you actually end up with a warping of the junction. And so you just kind of overheat that junction a little bit every now and then, and it actually lays that material back out flat again. So now this is kind of like online reconditioning. I don't know if you've been hearing the manufacturer say, oh, my stuff reconditions itself. Well, that's what they're talking about, is they've figured out this problem, and they're getting much better at it. Self-healing firmware. Okay, that's nice, but anytime that I hear auto-correcting circuitry, I start getting weird and think like Geordie LaForge, who said, oh, it must be a roving short. Last time I had electrical fire, it was in a particular location, it didn't move. Reboot decommission, I think I've already talked about it, so let's move on to the CPU. This is fun. The speed game is over, right? It leveled out, and now the game is on parallelization, cores, etc. And so you're looking at the first set of optimizations is the manufacturers are providing special libraries. Hey, you can use my special lock-in library, and you can do Fourier transforms faster than my competitors. So go ahead, use my library, right? This is very scary to me, but also does work really well. They know how to path optimize their own stuff, right? And then the low-power mobile market is making a really interesting disaggregation play starting to happen. You've seen the Calzetas and so on of the world start looking at what could you do with a truly low-power gob of devices that are all effectively networked together. So again, we're talking about the inflection point of networking and whatnot. I told you I would give you a little bit on the Xeon Phi, which, it's 64 cores in a single PCIe slot. What could possibly go wrong with that? It actually is really fast, right? It's extremely fast, about a teraflop. Only problem is there's almost no memory on this thing, right? Don't worry about the fact that you can't get any I/O to it or from it, but it has almost no memory. So anybody who's going to use one of these has to have an algorithm that's about this big and a data set that's about this big, because you can't get anything in there and you can't store anything in there. Oh, and by the way, don't mention that it burns 300 watts in a single card, and how in the world are you going to get that much airflow? So now you're basically setting a jet engine in front of your rack just to get enough CFM in order to keep your rack cool. Okay, loads and loads of in-card calculations. I hope you guys can figure out a way to use them, because I think, and my prediction is, this is the first of many moves where you'll see somebody actually go and cut the PCIe slot off of that thing and start making these as mini computers that you can then network together, maybe through, say, silicon photonics and this disaggregated rack I keep going on about. So look forward to that very much. Extreme power density is very hard to cool, right? The number of CFM that you need to use in order to get above sort of the 10 kVA, 15 kVA level is really very high. And that is actually a big problem, not only for humans who go and work in the data centers, but just in the log problem of the faster you move it, the more power you put into moving it, the more turbulence there is, the more stuff gets stuck on the pins, the more pins start to rust off. Just, it's a terrible thing. New libraries, etc. More threading, more cores. All these problems that we've already met, they're welcome, they're here. All right. With the last bit, reaching for better options. The open compute is primarily based around three things. It's a data center power design, and down here in the bottom right, you see basically a delivery system in a traditional data center wastes about 30% of the power that you put into the data center. So that is, if you're a 3 megawatt data center, you have a 1 megawatt of waste. And if you go instead to a newer power distribution, we've actually gotten that significantly below 7. We're down to about 4% losses now, which is really much, much better. And you know, transformers with their core saturation and all kinds of things like that. Then there's the data center design, which is what everybody was excited about, which is an open air exchange. Literally, I blow fresh air in through a bunch of atomizers who missed the air. So now my warm air suddenly gets moist and cooled by going through the misters. It comes into a cold aisle, blows through the machines, and back out one pass, never reused. Other people like Google, et cetera, choose the giant warehouse method, where this is actually a closed loop and doesn't actually spray the air, but the sprayers are outside and run a cooling coil in and cool inside. So now the difference between what this is called as a air side economizer versus the water side economizer. I bring the cold water in from outdoors, run it through some coils, and so on and so forth. Both perfectly useful methods. The open compute method is currently the air side. And here is a 2U. It's basically 1.5U, but the U's are slightly larger because we need better airflow servers. And you notice there are 3 servers wide in a regular, not quite regular cabinet. So if you look at an inefficient data center and move over, this is basically 17% of the data centers in the surveyed were very low efficiency, i.e. they had more power going to overhead than they do to the actual IT load, and 21% were highly efficient. If I could say, hey, I'll take half of your budget and turn it back into IT load, that makes lots and lots of people very interested. In 2009, Intel did this survey and basically came up with the concept of, here are what ASHRAE needs to come out with. And ASHRAE is the American Society of Heating and Mechanical Engineers, et cetera, et cetera. And so they're the ones who come up with the recommendations for how you can run your data centers, et cetera, and many other things. And they basically looked at where the world was at the time, and they did this calculation there. So in 2009, storage was 4% of all IT load. And if we cut storage in the year 2020, the power usage of storage in 2020, by 50%, that's the equivalent of having planted and survived 36 billion trees for 10 years. So these are not small numbers we're talking about. These are real things. This is the ASHRAE, and so the dark blue line that goes way up in the top, those are the NEBS compliant things. Those are things like the telco pops, et cetera. Facebook is this setup which is this light blue, but there's these others. The recommended is the old method in the center where we used to run our data centers, and now the tolerances go out much, much wider. An A1 facility, for instance, is just putting in some panels and baffles to get separation of your hot and cold aisle. A2, generally you find people doing a hot aisle containment and leaving the rest of the data center cool. By cool, I mean sort of like 25, 30 degrees C, 90 Fahrenheit, et cetera. That's considered cool in these data centers nowadays. The adoption is definitely happening. There is a lot of work that's got to be done because as the adoption of the ambient data center has happened, it's happened from people who care about power, not people who care about applications. So as you talk to any of these guys who go through, generally the market is about at stage 2, kind of starting into stage 3 now. DCIM is the hot thing that everybody talks about, and it has no ability to help us understand from an application point of view, where do I need to move my load? Do I have to move it to the other side of the data center because it's cold over there and hot over here? Do I have to leave the data center? Do I actually have to pause jobs? Am I going to turn off things? Lots of questions that have just never been brought to the application space. I wanted to drive a point home which is not understandable by most CFOs because it's a capital problem. These are power curves of 2 different power supplies. And if we say we're running in around an 800 watt load, and you look at the math here, like a watt plus tax costs about $19 a year. So if you look at the height to the trough of this one power supply, you're talking about $2,497 or $79 of actual waste in the data center because you bought a power supply that was how much cheaper? Certainly not $2,000 cheaper for a power supply. So there's a really interesting problem about trying to get the economics of I have to invest up front in order to save my operational cost. As we get into the ambient data center, failure rates are going to go up. If you've been in a cold data center, you would be at the 1.0. If you get into a data center that's at 95, you should expect basically 54% higher failure rates. Those failure rates are not going to be uniform across the world, depending on how you do all this work, et cetera. But qualification needs to be re-examined. How you do your qualifications are important. And there's another very hidden fact. The drives that were idle failed more often than the drives who were busy. Now, the theory that we're working on is that there's a diurnal temperature variance, and that diurnal variance is actually very bad for the drives, and that we should actually warm them up on purpose at night, right? Run your batch jobs at night, these kinds of things. So, okay, the reason I'm not going to go over this is because I'm already over time, and so I can't talk for a lot longer. The influencers. Storage is flatlining. Controllers are trying to get smarter, but they're getting enough hardware to become smart finally. So now it's the time for us to go whack on their heads and say, here's how to become smart for me. Memory is starting to forget why it existed. CPUs are getting foregoing bandwidth for IOPS, and so how are we actually going to feed it? Motherboards are breaking the monolithic barriers, and you're going to start seeing disaggregation. I will be a primary driver of it, thank you. And you're also seeing data centers becoming cost efficient, and therefore you have to start doing a different ROI on if I push this higher efficiency data center and have a higher failure rate, is the manufacturer going to do that all on RMAs, or am I going to take that and have to deal with it? Data classification, please start working on data classification. Think about the ability to take data from 3 replicas to an erasure-coded 1.4 overhead when you park it and not have to have so much replication, et cetera. And then virtualize the data center, not just the data. That's what's really starting to happen. And you're starting to look at the disaggregation of racks. You're looking at, yes, You can only put 7.5 megawatts in a facility because that's what fire code says. That's what an aluminum smelting plant is allowed. There is no known thing that can take more than 7.5 megawatts. That will be your limit until somebody manages to build something bigger than 7.5 megawatts, and then it will be the new standard. So, forgive me for going over.
Thank you very much.